Hello, welcome to Rust Shorts. These are short videos, usually under 10 minutes, that focus on a single topic in Rust. In today's first short video, we're going to make some comparisons with Rust with some other common programming languages you may be used to, like C++ and C# and Java. I have here a URL for this page. There's quite a few links on this page that we're not going to explore. So I've provided this so that you can open the page and explore some of the materials that we link to, after the video is over, or, concurrently while you're watching the video. Okay, so with that, we're going to cover the material. We're going to skip over a lot of the material on this page, and we're going to cover the material in Table 1. And that focuses on things that Rust omits, that it changes, that it requires, and it supports relative to other languages, again, like C++ or C#. First of all, Rust omits garbage collection. Rust makes guarantees by construction of memory safety without using garbage collection. And that has the outstanding advantage of providing memory safety by contract without the performance penalty that garbage collection entails. Rust eliminates function overloading. Rust classes Rust constructors do not take the name of the class as they do in C# and C++, for example. So there's no need. It's not required to have function overloading, and so Rust has chosen to keep things simple and not implement function overloading. Rust does not provide inheritance of implementation. Rust provides for inheritance of traits, which are very similar to C# and Java interfaces, but it doesn't support inheriting from a base class. So C++, you can inherit from multiple base classes. In C# and Java, you can inherit from a single base class and multiple interfaces. In Rust, you can only inherit from the traits, the interfaces, if you will. You can still do polymorphic operations using the traits, as you can with these other languages. The one thing you can't do is directly build deeply nested inheritance hierarchies. And these days, the OO community seems to be coming around to the point of view that deeply nested hierarchies are not a good idea anyway. So I haven't missed it. I've written quite a bit of Rust code lately, and I don't miss not implementing inheritance of not providing inheritance of implementation. Rust eliminates implicit conversion between types. You can convert using methods. The library types and your own custom types can have conversion methods, and they work just fine, but they have to be invoked explicitly. So there's no surprises. Oh, gee, this converted to, I didn't expect that. And that doesn't happen. Rust eliminates dereferencing raw pointers outside of unsafe blocks. Unsafe blocks are small pieces of code, usually just a single function, that are intended to allow you to interface with code from other languages, especially C. And occasionally there are times when it can be difficult to do some particular thing without resorting to unsafe blocks. But as I'll mention in just a minute, you can avoid most of that. Basically, the need for unsafe blocks is taken care of by types provided by the standard library. They have, many of them have unsafe blocks to allow operations that would normally be disallowed because of the need to keep a contract for memory safety. And those in the standard library are very carefully vetted to ensure that the interface to that unsafe block is absolutely memory safe. So, instead of you using unsafe blocks, you can use the library types to do the kinds of things that you need to do without you directly implementing unsafe blocks. And that's a really good idea, because the team, the Rust development team, are very expert at these maintaining type safety, and so let's let them, we'll use their expertise. So that works very well. And I've written quite a few thousand lines of, many thousand lines of Rust code, and I've never been forced to use an unsafe block. Rust changes types into two. They divide their types into two classes: copy types and move types. Copy types are only types with contiguous memory. That means the primitive types and aggregates of other copy types. Move types are everything else. For example, a string has a control block on the stack and character data on the heap, and so it's not contiguous memory. Same is true of vectors, same is true of maps, and so on. Those are all move types. With move types, when you construct or assign or pass by value or return by value instances, they are all moves. What that means is that the resources of the source are moved to the destination, usually with just a single pointer copy, very fast. But the source now becomes invalid. If you can pass by reference just fine. Passing by reference does not do a move. It simply copies a reference. It doesn't attempt to copy the object. Most of what you do, very often, a lot of my code, the reference use is primarily passing and returning by reference. So, that works really well. And there's another escape clause coming up in just a minute. Semantics for copy types and move types are fixed. That means that you can't change the way the copy operations and move operations work. They're fixed and determined. You don't have to, and you can't implicitly define copy and move constructors. There are no copy constructors. There are no move constructors. All of that is built into the basic type system. And so, Rust definitely provides for construction, definitely provides for assignment, but under assignment, copy types are copied, move types are moved. Rust supports deep clones and defines a clone trait, and any type that implements a clone trait can be copied by calling clone. Clone makes a deep copy of that type. And almost all of the move types provide the clone operation. So, anytime you really want to make a copy, you can use the clone operation, but you have to do it explicitly. Copy is never done with a move type, never done implicitly, is always done explicitly with a clone operation. Rust enumerations have elements that may wrap instances of other specific types. That turns out to be very useful. You can dig into that a little more with the links over here on the right. For the sake of time, we're going to move on. Rust enumerations are often used with a matching syntax, And the matching requires that you look at each of the enumeration types and handle them appropriately, so you can't forget to do one or defer one for later and then never get around to providing it. And again, that's discussed in these links. Rust iterators are very similar to C# iterators. They have a lot of predefined adapters. You'll see a lot of iteration and adapter methods being used in expert Rust code. Strings have their own iterator over their characters called chars. It has a different name than the other iterators, and we'll explain why in just a minute. What Rust requires. So what Rust requires: explicit declaration of mutability. Data is not mutable or immutable, but the variables that manipulate it or references that manipulate it are either mutable or immutable. That means they're either allowed to change the value or not. They're either allowed or not allowed, depending on whether they're mutable or not mutable. And by default, they're not mutable. You have to explicitly declare the mute keyword. There's no concurrent aliasing and mutation with references. You cannot share mutation with references. That's the prime constraint that Rust imposes to so that it can offer this contract for memory safety. And that's a strong constraint. Essentially, a Rust program can't read or write to memory it doesn't own. I mean, that's a good thing, obviously. But it means also that it's difficult to build linked data structures in Rust. Almost always you try not to. It's very common to build what you'd ordinarily think of as a linked data structure with a vector. For example, you can build a graph class by putting vertices in the vector and then using indexes to represent child relationships or parent relationships between those vertices. So very common. References must not outlive their referends. That means there's no dangling pointers. Rust has what they call a borrow checker. People that write a lot of Rust call references borrows because you're borrowing the ability to view and mutate values owned by another instance. So Rust compiler's borrow checker analyzes reference lifetimes and refuses to compile cases it can't guarantee won't meet this invariant that that the references lifetimes are strictly no larger than their referends. Usually it can do that silently. Occasionally it'll ask you, it'll fail to build and say that it needs you to annotate lifetimes so that it can offer the guarantees. That's very rare. The borrow checker is really good and getting better all the time. So there's only one owner of data. When that owner goes out of scope, the data is released. And the safeness guarantees a guarantee that there are no outstanding references when that data is released. Direct access to heap storage uses a smart pointer called box, and when a box goes out of scope, it releases its allocated storage. Function invocations on a generic type. Rust does support generics. It supports it in a quite simple way, very nice way, very much like C# and Java implement their generics. And like C# and Java, if you call a function on a generic type, you have to be bound by a constraint that guarantees you have that function. That the type you're calling on has that function. And here's an example. So f of demo, where t is clone, because I bound it by this constraint that t has to satisfy the clone constraint, then I can call rt.clone in the body of my function. That's the way it works. Things that Rust supports. Rust supports error handling with the enums, result, and option. Error handling is really very pleasant, very powerful in Rust. And it's a consequence of the enumerations we talked about before. We haven't said enough for you to really understand how that works. But again, the links over here will take you into all that. Rust strings are a collection of UTF-8 characters. And that means that the characters are not a single size. They vary in size from 1 byte to 4 bytes. And that opens a very large set of possible characters. And that means that now Rust can support things like kanji and Arabic characters and diacritics, and those kinds of things, so that Rust programs can be written to work for users that know a non-English language. Function types, function and type declaration definitions may be ordered without concern for dependencies in a single file. You don't have to declare before use, or you don't have to define before use. It can be anywhere as long as it's in the same file. And C# and Java work the same way. Panic on integer underflow or overflow in debug modes. A panic is an orderly shutdown of the thread on which it's found. So if it's on the main thread, it'll shut down the process. And that's a good thing. What that means is that you can't propagate this incorrect value, the overflow value, into your computations without realizing it. The Rust standard foreign function interface library, FFI library, provides strings that have wrappers for the standard platform strings, and it provides pathbuff and path, which wrap those OS strings, adding methods for handling paths. All this is designed primarily for foreign function interface. And the last thing is kind of interesting. Rust can generate WebAssembly. I haven't had the chance to look at that in any detail, but it looks like it'll open some really interesting possibilities, and I'm really looking forward to getting the chance to look at how all that works out. All right, we're going to stop here. I hope you've enjoyed the video, that you'll enjoy working with Rust, and that this video has helped you get used to the Rust language more easily than you might otherwise. So with that, until the next recording, I will say adieu. Goodbye.